not in the textbook, but I think it's interesting. I would like to show this to you. Last time we covered the Taylor series, and then I'm going to use this to prove the Euler identity, which consider the most beautiful equation in mathematics. You have E is irrational, you have I is imaginary number, you have pi is irrational, you have 1, add 1 is a whole number, it's a real number, it's an integer, and you end up with nothing, it's just 0, which is beautiful. Anyway, I would like to show you the proof of this. Again, it's not in the textbook and it won't be in the test. So if you remember, Macaulay polynomial is come from Taylor series of polynomial when you let c equal to 0. So you have f of 0, take the first derivative, times x, divide by 1 factorial, second derivative, x squared, 2 factorial, divide by 2 factorial, and so on. So I'm just going to put in 3 little pieces first, and then we put it together. So the first function I would like to talk about is f of x is equal to e to the x. And if you apply to Macaulay polynomial, so you're going to have this whole series, all right? When x is 0, right? And the first derivative, e to the x, is just e to the x. Second derivative, still e to the x, and so on. So x is 0, that's why I have all the 0 here. E to the 0 equal to 1. So my first term is 1, and the second term will be x, the third term will be x squared over 2 because 2 factorial is 2, 3 factorial is 6, and so on. Since I have this one, I'm going to replace x by ix, alright? I is imaginary number. So I end up with this whole series. Now if you remember, I is imaginary number, I square is -1, I to the q is -I to the 4th is 1. So I replace all that in this series. So I end up with the first equation here. So I'm going to leave the first equation here for now. We're going to come back to it later. Now I create another function, f of x is equal to cosine of x. Again, I apply Macaulay polynomial, cosine of 0, derivative of cosine is negative sine, and so on. Plug it in the formula. Sine of 0 is 0, so everything that has sine of 0 will go to 0. Cosine of 0 is 1, so all of cosine of 0 will be 1. Then I will end up with this second equation right here. Again, let's leave it here for now. Now I'm going to create another third function, f of x equal to sine of x. Again, apply Macaulay polynomial in there, so sine of 0, derivative of sine is cosine, and so on. Now all the sine of 0 is going to be 0, so I have 0 here, 0 here, and 0 there. Cosine of 0 is 1, so I will have x squared for this term and x to the cube for this term. And I just simplify my 3 factorial. Simplify all this, and then I multiply this function by I. I multiply sine of x, which is this, by I, and then I get this. Alright, so let's call this the third equation. Now I have the first, the second, and the third. Alright, so remember my first equation right here, over here, I'm rewrite it over here. This one is equal to e raised to the ix. Now I group them differently. As you can see, the first one, the third one, and the fifth one, I group it here, and then I group the rest here. As you can see, this series is just I to the x, and the first group here, you can see it's just my second equation here, my second series, which is cosine of x. And then this group that I group, it's just I sine of x. Now what I did is I replaced the x by pi. So I have I pi equal cosine of pi plus I sine of pi. So e I pi cosine of pi is -1. Sine of pi is 0. So I have this, and I add 1 to both sides, and I end up with my beautiful Euler identity equation, the most beautiful equation. Bye.